course. Otherwise, I can risk breaking it in half. While I don't usually wear gloves in my videos, I'm wearing one this one because this stone was so big. It's also important that I'm protecting my leg with leather pads during this process. We're getting closer to the finished blade, so now I'm using smaller tools to sharpen and shape the blade further. To finish the blade, I use deer antler to sharpen it, as well as create the tang for it to fit properly in our antler handle. The tang in the blade also allows me to wrap it securely to the handle with deer skin. I made sure to make this knife thin and really sharp, so it'll work well to fillet a fish. In this video, I'm going to
चेंजिंग अगर आपने कभी सोचा है जहाँ नॉर्मल हाईवे के रोड इस काले वाले डामर से बनाए जाते हैं वही टोल गेट के पास रोड कंक्रीट से क्यों बने होते हैं दोस्तों ऐसा इसलिए किया जाता है क्योंकि डामर वाले रोड में इलास्टिसिटी तो बहुत होता है जिससे हम गाड़ी चलाते समय स्मूथ और कंफर्टेबल फील करते हैं लेकिन इससे बने रोड की बाइंडिंग रेजिस्टेंस ज्यादा नहीं होती टोल गेट के पास ज्यादातर गाड़ियां हाई स्पीड में आकर अचानक से ब्रेक लगाते हैं और यहाँ कई बार गाड़ियों को रोकना और चलाना पड़ता है
Good afternoon, students. So today we will continue further. Any doubt in yesterday's class? Okay. So today we will be starting with yesterday I have given you an idea of what is the resemblance of qubit and what information how to represent the information taking two bases. The bases are in the z-axis defined as 0 and 1 in the vector form, and they resemble as north and south pole. Okay, now let's have a look on measurement in the other bases. That means when we are considering the Bloch's pair, the qubit can be represented any of the bases. Presently we are working on the axis, and I have discussed till yesterday only the z-axis. Now we will be discussing x and y and a general basis. That means if that base is a valid one. And what is the condition for valid one? For 0, 1, what was the condition? The condition was if they were on the opposite spin, or simply if I talk the angle between them was 180, you can say, or they are on the opposite side. So any, like for the x-axis, one is the positive x-axis and negative x, so they are on the extreme side of the sphere. So any base, any thing can be able to become a base if the points defining them are on the extreme side of the sphere. So let's see how the conversion is done to other bases. Measurement in other bases. Your Z basis normally when you write bases, we always write in curly braces. In curly braces, the order does not matter. It simply says that it is. But when we write in a normal round bracket, we define that this is defining the positive one and this is defining the negative one. That means Z base, when you write bases, you can write the order can be exchanged if you are put in the curly braces. They are defining what are the orientation. But when you write it in a vector form, it comes that it is positive direction and negative direction when you define a qubit. And vector direction matters a lot. Okay, let's take for conversion. Let's take an example. Suppose we have a qubit. Suppose we have a qubit defined in Z basis. Root 3 plus 1 upon 2. This one. So if I define it, if I link it with the coordinate or the orientation wise, if you remember the last class, it was your r cos theta was your x and r sine theta was your y. And we all know normally r square is equal to x square plus y square. So if I say your cos theta, because when you sum both of them it is going to come 1. So r, if you say root 3 by 2 cos square plus 1 upon 2 square is equal to 1. So that gives r is equal to 1. So that means your cos theta is root 3 by 2, or we can say theta is 30 degree. This you can verify for the other one also. So that means this, if I talk about this, the point is more nearer to x-axis. Or you can say this point is, if I draw on the block sphere, this is my x-axis. Now you just we can think of like this. Simply the point is here, that from the x-axis it is making 30 degree. In the 3D vision you can understand it is making, the point is here, somewhere here, making 30 degree from the x-axis. Now you have to write this in the form of x-axis basis. That means in this point z-axis bases are coming. I have to represent the coordinate now in the plus, minus, or x-axis. So how it is done? So what we will do, yesterday I told you so this is 0, and if you remember, I suppose in the last class we had this thing. So plus is, this was the plus. Yesterday I told you it is midway between 0 and 1. So when we solve this equation, when you are going to solve this equation, you will be getting this 0 or plus and minus in the form of sorry, what I want to say is that yesterday we have done this thing. The plus was plus axis was halfway between 0 and 1, north and south. So this was the representation, and your minus x-axis was this one. So from, if I solve it, I can get 0 and 1 in the form of this. And how I have solved it, this also we can go. Simply multiply the first one. Normally it is the multiplication by the conjugate, complex conjugate, but they are normally numbers, so complex conjugate will be the same number itself. So it will be okay. Now simply when you add these two, you will be getting the value of 0. Is it clear? And simply when you subtract it, this is. So this is how I have represented 0 and 1 in the form of plus and minus. And this we have discussed in yesterday's class, if you remember. That plus minus means it is halfway. And from this, what I have got 0 and 1 measurement in the form of plus and minus. I suppose this conversion is clear to all. Or the simple way I will be telling you is that what you will do, whatever is the multiple of 0 in both the representation, multiply this number by their complex conjugate. I will be giving you a general solution also, but for now, because the complex conjugate sign will not change here, so it will be simply that number what I have done. Okay. Now come back to our original qubit that you have to represent in plus and minus. So how will you do it? Simply your bit qubit is root 3 by 2, 0 plus 1 upon 2, 1. Now just substitute the value. You have got these value, substitute these values. So it will be root 3 by 2, 1 upon root 2 plus 1 upon 2 plus 1 upon 2, 1 upon root 2 minus 1 minus 1 upon root 2 solve this one. So it will be root 3 2 root 2 plus 1 upon 2 root 2 plus next one you can say root 3 2 root 2 minus 1 upon 2 root 2 minus, or in a simple way if I say it is root 3 plus 1 2 root 2 plus root 3 minus 1 2 root 2. Is it clear? So how have you got it? Now, is it a valid quantum bit? You have to check the norms. It should, the probability amplitude square sum should be equal to 1. So this is alpha, this is beta. For it to be a valid, what we require? This should be 1. Let's check it. So simply it will be 4 plus 2 root 2 root 3 divided by 8 plus 4 minus 2 root 3, so which is equal to 1. So yes, it's a valid qubit. Now probability of plus 1, it is equal to, if I simply solve it, so it is 4 plus probability in plus 1 upon 2, so you can say 2 plus root 3 upon 4, and if you will solve it you will get the value as 0.93. And yes, when we find out the angles and all, 30 degree near to positive x-axis, and now you can have the probability. Simply when you will find the probability of in minus axis, so it will be 3 minus, sorry, it is 4 minus 2 root 3 divided by 8, which is equal to 2 minus root 3 upon 4, and which tends to be 0.07. Is it clear? This conversion is clear how I have converted the base from 0 1 to x plus and minus. That means the basis for x axis. Any confusion in this? Okay, we will do for one more. Maybe it's new one, so you get more clarity with the next one. And if there is out, I will be doing again for the y-axis basis. Now let's see. Y-axis bases are, these are your y-axis bases. And how can we represent these y-axis bases? Okay. Yesterday we discussed that you can represent as iota, which is 1 upon root 2 plus 1 upon root 2 iota 1, and the minus 1 was 1 upon root 2 plus minus iota by root 2 1. Okay, now when I want to represent them or convert them as in a form of 0, or you can say 0 in the form of iotas, how will we do it? So yeah, 0 is, the first one is root 2, 1 upon root 2 conjugate is the same one, iota. Here also no change. It is and your 1 will be now. Just look at this one side. I will just give you an idea. See, for 1 we will be multiplying it by complex conjugate. It's iota, so it will be minus iota root 2, simply the first one, that is your iota, plus what is the complex conjugate of this? The complex conjugate is iota root 2, and the base is this. Is it clear what I am doing in this? It's a new thing. See, again I am telling you, for converting it to any bit, if it is given in 0 and 1, what will you do? You will find how 0 and 1 can be represented in the base that you require. And for getting that in the base, what will you do? Just look at the original representation. For the 0 1, just focus on these parts, at both 0 1. What will you do? You will multiply left hand side on the complex conjugate of the multiple. See, it is 1 upon root 2, 1 upon root 2 in both sides, so complex conjugate will be same, nothing. Next come for the 1 1. If I'm talking about the 1, I will be focusing on these two parts. Here the coefficient is iota 1 upon root 2, so I will be multiplying it by its complex conjugate, and its complex conjugate is minus iota 1 upon root 2. Here it is minus iota root 2, so the complex conjugate will be iota upon root 2. So this is how you have represented in 0 1 in the basis of plus iota and minus iota. Got it? So what we are doing, we are simply first of all transform z basis in form of required basis by multiplying with their complex conjugate. Okay, now let's come to our original question, the qubit that you have to represent. And your original qubit was this was your original qubit. Now to transform it, just simply substitute the value. Root 3 by 2. What is your 0? 1 upon root 2 plus iota plus 1 upon root 2. Now next is plus 1 upon 2. So it is minus iota root 2. Okay. Now think for this iota terms. So it will be root 3 2 root 2 minus iota and next one is plus root 3 plus iota 2 root 2 minus iota. Is this representation clear? This conversion is done. Again, if you find probability of getting iota is which is equal to 3 plus 1 divide by 8. Any idea how why I have written like this form? It is also 3 plus 1 upon which is 2. So that means it is exactly for the y-axis, it is on the equidistance because it is having the inclination with the x thing. So for y, it's having a 90 degree or in an equidistance mode. Is it clear? Today, no question I'm getting. So are you not getting or anything is missing or my voice is not clear? Students? Are you able to understand? Or if there is anything lacking, you just ask me. Okay. Maybe the topic is tough, that's why you are. Now let's do a general question on any basis. Now suppose we have two states. We call it as A and B. Your A is root 3 by 2. So now these are two different states. Simply, if you just check the angle, it is 30 degree above the y-axis. Now it is iota, definitely will be above the y-axis. And this is below the y-axis. So they are located on the opposite side of Bloch sphere, so they are valid. Now again the question comes, you have to represent the given qubit in the form of A and B. So how will you do it? Simply represent 0 and 1 in this form. So I will be doing it. We can do it directly also. We can do by this. So root 3 by 2. So it is this. Root 3 by 2 and the other one, the complex conjugate. And for the 1, it is minus iota by 2 plus okay. Now the given qubit your given qubit is equal to plus 1 upon 2 okay. So when you are solving it, it will be 3 minus iota by 4 a plus root 3 1 minus iota upon 4 b. If you want to find the probability, here also you can do the same. Probability in A is equal to 3 minus iota norm square, which is equal to 3 minus iota upon 4 into 3 upon 16, which is 5 upon 8. And for the other one, probability of finding in B will be root complex conjugate, which is 3 upon 8. So this is how you can convert the given qubit in any basis to another basis. Now I'm giving you one question for your trial. The question is, now suppose we have two states. And the question is, how can you measure qubit psi is equal to 1 in term of A and B, and the second part of this was see measure probability in each. And I request you to try this question because see it's a new thing. Students, are you understanding? Because today I'm not finding any response from you. And yesterday class was very much interesting. You were just asking the doubts and all. Clear, ma'am. Okay. So if it is clear, it was a previous one. So just try this question. I think most of you are on a holiday mood today. Okay. So normally qubit is a probable state. Normally we say it is this configuration, that means it is the finding probability on this axis or on this is this and this. We are not when you define a qubit of
एक्सक्यूज मैम
हाँ जी बच्चा
मैम ये लास्ट क्वेश्चन का आप एक बार आंसर बताओगे मैम प्लीज कंफर्म करना था
वेरी गुड, आई वाज वेरी हैप्पी फॉर डन इट. हाँ बिल्कुल बताती हूँ बच्चा, लिख देती हूँ. विल राइट द आंसर. आप वेरीफाई करो, इफ नॉट द सेम आई विल बी जस्ट.
मैम ये क्वेश्चन में ये जो बी वाला है वेक्टर ये i/2 0 वेक्टर और 3/2 1 है ना.
3/2 1, yes yes yes, keep typing there. So this is the answer, this, and the probability in A is 3/8.
Ma'am, can you solve this question, ma'am? I am getting wrong answer.
Okay. A is I have written the same one. Okay, now first of all represent in this 0 and 1 form. So your 0 will be root 3 by 2 a minus iota by 2 b. Okay, and your 1 will be minus iota by 2 a plus root 3 by 2 b. Okay, now your given qubit is 1 upon 2 0 minus root 3 by 2 1, so it will be 1 upon 2 root 3 by minus iota by 2 b minus root 3 by 2 minus iota by 2. So when I simplify it, it will become root 3 to root 2. Sorry, it will be 4. Root 3 by 4, and here it will be coming as plus minus, no, to minus minus iota. It will be plus iota a, and the second one will be plus minus iota, and this side will be minus root 3 by 4 b. Got the answer, बच्चे?
मैम यस क्लियर मैम. मैम इससे पहले वाले क्वेश्चन में जो आपने दिया था जिसमें a वेक्टर इक्वल टू रूट 3 by 2 0 प्लस i इंटू 1 वेक्टर और b इक्वल टू i by 2 0 प्लस रूट 3 by 2 1 वेक्टर, इससे नेक्स्ट पिछले वाला क्वेश्चन मैम जो आपने सॉल्व करने के लिए भेजा मैम, इससे पिछले वाला
यही वाला क्वेश्चन है बच्चे, यही तो सॉल्व किया मैंने.
यस मैम. मैम इससे पिछले वाले में एक डाउट है मैम, इससे बैक वाले क्वेश्चन में. यस मैम.
हाँ बोलो.
इस वाले में मैं आपने जीरो को कैसे एकदम से इसमें कर दिया, ए में कन्वर्ट कर दिया.
यही तो मैं बता रही हूँ कि कन्वर्ट करने का तरीका सीखो इसको, बिकॉज डायरेक्टली अगर एल्जेब्रिक एक्सप्रेशन से करोगे तो टाइम लगेगा. बहुत सिंपल सा मेथड है. देखो मैं मेथड बताई थी आपको. फोकस ऑन दिस, यू हैव टू राइट जीरो टू फोकस ऑन दिस जीरो पार्ट. ठीक है, करना क्या है, जो जीरो के मल्टीपल है वो दोनों देखो और ए और बी को इनके कॉम्प्लेक्स कॉन्जुगेट से मल्टीप्लाई कर दो और सम कर दो. अब रूट 3 by 2 का कॉम्प्लेक्स कॉन्जुगेट क्या होगा, रूट 3 by 2. ठीक है, अब इसमें आ जाओ. तुम्हारा इसमें तुम्हारा फर्दर अब इसका लोगे, इसका कॉम्प्लेक्स कॉन्जुगेट क्या होगा, माइनस
i by 2.
मैम
यहाँ पे तो फिर ये रूट 3 by 2 a होगा और फिर माइनस i by 2 b नहीं होना चाहिए.
कर दिए, ये मैंने लिखने में गड़बड़ कर दी है, कॉमन नहीं लिखना था मुझे, ये ऐसे है
मैम. यही क्लियर करना था मैम.
अच्छा
मैं इसके वजह से नीचे वाला पूरा गड़बड़ हो गया मैम.
ओह अच्छा हुआ तुमने बता दिया, सॉरी. मैंने सॉल्व बिल्कुल ऐसे ही कर दिया है, लेकिन यहाँ गड़बड़ कर दी लिखने में.
मैम इसलिए कंफ्यूज हो गया था लास्ट नेक्स्ट क्वेश्चन में.
ओके. हाँ. अब समझ में आ गया?
यस मैम, अब आ गया मैम.
सॉरी. अच्छा मैं मॉडिफाई भी कर देती हूँ. कम से कम तुमने पिन पॉइंट तो किया, otherwise no one pinpointed it, and that is simply an error. This is big. Yes.
Okay ma'am.
Thank you for pointing the error. चलिए next करते हैं. So it is consecutive measurement. Normally when you have the quantum bit, we define what is quantum bit. It's a simply a probable state. That means it has this probability on this one. Or if I talk about the global position, that means it is having this much angle, this is the orientation. So currently we are talking about the Bloch sphere of one radius. So we simply give the orientation that it is this much angle with respect to x-axis, or this much angle with respect to y-axis, or this much angle with respect to the basis that you have chosen. But you choose a baseline with this thing. The thing is, the moment it's when till you are not doing the measurement, it is in this probable state. It is simply like when you are spinning the coin, it is in probable state. The moment the coin fall down, the probability ends, and simply you collapse in one of the states. So normally when you perform whenever you do the measurement, the qubit collapse the state to whatever we measured. That means simply if you are measuring in z axis, so it will simply collapse in the state 0 or 1. If you are measuring in x basis, it will be collapsing to 0 plus or minus, or like that it will be collapsing. So in that case, it is normally having a 50. Whenever we measure it in that, it is like a halfway. The probability normally we say it's half, or for any other qubit, it can be any numbers between this and this. The moment it has collapsed, now what will happen? If I ask you now what is the probability, now it is not a probability, simply it is a confirmed situation that when we do after measurement, if we again repeat it, or if I again ask it, then the state to which it has collapsed, we say the probability is 1, and the other state the probability is 0. So simply if you further, it is the moment we measure it, it is not in a probable, now it will be in a simple state that we call it as final state. The probability ends at that point. Okay. Now this was the basic representation of qubits or quantum bits. Now next we will be discussing it. I have to discuss the spherical coordinate that we'll be discussing with one. The point will be requiring. But now we will be moving to next concept, that is quantum gates. So because we are moving from classical computing to quantum computing. So, and if you all are aware, in the classical, every operation, and if you we study the digital one and all, what we are doing actually, all that is represented is all operation are done with the help of gates like and or not. Basically these are three. Then digital, you have studied that NAND gate is considered to be as universal gates, because every operation was able to be implemented using NAND gate. And this was how classical computing, or the era we do computing, exist. Now when you are moving to the era of quantum computing, we need to define that how we can design the gates, because the gates give you method of doing the operation. The first part is that quantum is has a good part, that one electron you can store multiple information, so the dimension of information storage increases in quantum. But just having this information has of no use when not you cannot do any processing, and you cannot get. So for doing this processing in classical, gates play an important role, and that is why you studied in computer architecture. If you have studied all the circuit, even it is adder circuit, subtractor circuit, sequential circuit, combinatorial circuit, the base was all of the circuit was what? Gates. So similar thing we are going to study in this quantum gates also. We will be studying how they are different and how we can design it. And then I will be discussing a basic circuit also. This and quantum is an topic, or you can the subject, which is evolving. It is not on the final state. That means whatever the scientist or the research is going on, to implement the existing classical computing algorithm in the quantum. So that is why there are many things going very less known wherever the work has been done, because till last 3 to 4 years back, all the work was done in only by the physics professors. If you will study the books or not, it is like quantum mechanics, because the challenge was, the thing is how, because this all asked magnetic moment and all this information of electron level particle is stored, and we all know we have out atmosphere all these radiations, so they can change the electron orientation or the spin direction, and it is very highly, like a stage you cannot control at minute level. So that is why current the physics person are going. Now the parallel has research has been started with the computers and the electronics person to design all the approaches or the circuits we were having in classical computers, that to be in this. So that is why this all gates and everything is being on the, and we will be discussing this in the course, how the quantum adders, yes, quantum adders also I will be discussing, quantum gates, how the operations are performed. Okay, so let's start with quantum gate. So simply there are some condition with this. What is this? Let's have a look. Quantum gates, they act on qubits like logical gates act on bits. What does it do? Quantum gate transform the state of qubit into another state. For example, we have a gate U. What it does, it performs the following map. And when bit 1 is given to this, it will be doing this one. Normally the gates were designed for some operation in classical gates. On was to, not was to reverse the bit, and was when both the bits have been give the answer as 1 if both are any one of is 0. So that was a logic design to do some processing in the classical computing. Similarly, the quantum gates are also designed. So suppose one of the gate is having this mapping. That means when you have the bit in 0 phase, do this thing. When it is in this, it must be do this thing. So it is just how it is and what help will be doing it. First of all, let's understand the question. The condition for a quantum gate is, quantum gate must be linear, that is, it can distribute it across superposition. What does it mean? That means because our qubit is not a 0 or 1, it's a superposition. So the gate should work on a superposition. That is the requirement. In what manner? Simply, it's like what it? So that means if it is alpha multiple of zeros phase and y, so simply it can work on this manner. The second condition is, it requires total probability must remain 1. Whenever you apply a classical gate, what you require. The bit should be in 0 or 1 state. If it is anything other than, it is of no meaning. So that is the case. But when if I'm applying a quantum gate to a qubit, the answer should be a qubit. It should not be anything random. And what is the condition for a valid qubit? Say the sum of probability amplitude is equal to 1. So let's check for this case. Is it valid or not? Whatever is given to us. When I apply this u alpha, it will be simply alpha root 2 minus iota upon 2 minus 1 upon 2 plus beta 1 upon 2 0 plus root 2 plus iota upon 2 1. Further, when we solve it, it will become alpha root 2 minus 1 upon 2 plus beta 1 upon 2 plus minus alpha by 2 plus root 2 plus iota upon 2 beta 1. Clear? Let's check for the probability amplitude. So it is so simply for this normal amplitude multiplied by its complex conjugate. So it will be alpha square root 2. It will be 2 plus 1 upon 4 plus beta square by 4 plus alpha square by 4 plus beta square by 4, and simply if you sum it, it will be alpha square plus beta square. And we all know that the original bit given to us, this was our original quantum bit, and this quantum bit was having the condition as this. Our original quantum bit was what? Alpha 0 plus beta, this one. And on this bit only I have applied the gate u. So just see, if I check the probability amplitude, it turns to be 0, 1. So normally this mapping is an example. This is an example of that this is a valid gate. You have designed just a gate. We will be having different type of gates. Now I'm just saying this is a gate, and what is this gate doing? This is doing this transition in the basis of 0 and 1 given. To check this gate as a valid one, we have it should satisfy two conditions. First, it should be linear. That means it should be distributing the operation across the superposition. That means it should be valid on all the superposition state. And second, the total probability should be 1. Or in the second one, whatever is the result of the gate, that the result should be a valid quantum bit. Is it clear? So in tomorrow's class, I will be just discussing what are the different type of gates in quantum. I've given you an idea of what is a thing. Okay, just let me give you one question also. And this is the today's task. Just do it. In tomorrow's class, I will discuss the solution if you're not able to do it. There are simple questions. One simple question is, again, we have a U gate, which is doing this transformation. You have to check whether this gate is valid gate or not. And second, So check for these questions whether it is a valid quantum gate or not. So for the first one, you will get the answer no, it is not a valid gate. While this, you will be getting the answer as yes. And this is, I'm just giving you a hint. Just try these two questions, and tomorrow I will be discussing if you find any problem. And tomorrow we will be working on the actual gate. This is just I've given you the introduction of what is quantum gate and what condition a quantum gate should satisfy. Is it clear? Okay, so I will be sending you the notes. Anything else you can ask me. Uh, Try to do this question. Tomorrow, okay, I will be just talking with Arden. Or if there is any favorable time, you can tell me.